Out for the first few seconds. So this work basically came about from Steve and Tom and my advisor Luke Olson and Jacob talking at the Multigrid Summit, and they started to notice that maybe p-ideal isn't the most ideal for a coarse fine splitting. And I've had the pleasure of carrying on some numerical experiments to further flesh this out. So without further ado, so our motivation, we want to solve efficiently AX equals B, where A could be a variety of problems. And we'd like to do this with a principled linear solver. So in terms of efficiency, we think of multigrid, where the coarse grid correction term right here requires that the relaxation on the error is in the range of our prolongation operator. And we're really interested in this interplay between coarse grid correction and relaxation. In terms of the coarse grid correction, we look at our prolongation operator, and this is going to affect the amount of work we need to do in two ways. First, if our prolongation operator is very accurate, we should have a faster convergence rate. But if it's too accurate and possibly very dense, then the Galerkin product will also be dense, and it will take a lot of work to solve. So we want to balance this. All right. And then also we have the weak approximation property, which gives us an idea of what we would need in order to have two-grid convergence. And so to get p-ideal, we actually formulate this as an optimization problem, and we solve for beta. There's a couple of things about this that you might have heard yesterday, but just to do a brief review, we require certain properties of our restriction and prolongation operators. P needs to be full rank, RP needs to be the identity, and in particular, we form a new matrix S, and R and S form an orthogonal decomposition of Rn. This allows us to rewrite our error in terms of S and R, and so when we plug this back into the weak approximation property and chug through the algebra, we basically find that P is minimized when P transpose AS is the zero matrix. And by doing more algebra, we can find a form for P. By taking this clever choice of S and R transpose being the identity, this is how we get p-ideal, which is negative AFF inverse, AFC. So these are the weights, how we interpolate the coarse grid back to the fine grid. And then this is the identity or injection. So we're injecting the coarse points to and from the fine grids. And here A is just written in terms of its fine and coarse grid variables, respectively. Okay, thanks. All right. So what is our objective here? Our objective is to see how this ideal prolongation operator performs computationally compared to some existing multigrid methods. And we're going to look at this in a variety of ways. How is the weak approximation property minimized? What does the convergence look like? How is the operator complexity? And one of the big things in this talk is how do these prolongation operators appear visually? So just to do a quick review of some of the common interpolation schemes that you'll see in algebraic multigrid. This first one is just classical ANG. So we have our CS splitting. Every coarse point gets a basis function or column in our prolongation operator P. And here that's just given by direct interpolation. So you can notice that we can rewrite this in a form similar to the ideal prolongation operator, where the identity is at the bottom and our weights to interpolate the coarse grid variables back to the fine grid are at the top. And actually, as it would turn out, for the 1D Poisson problem, this gives you your ideal prolongation operator. All right, so with smooth aggregation, we begin by forming a near null space candidate, or some idea of the smooth error. In this case, I just took the constant vector and relaxed on it with Gauss-Seidel. I then formed the tentative prolongation operator from that candidate, requiring it to interpolate it. And then we can improve on this operator by relaxing on the columns of it. So here I just improve it with weighted Jacobi. And you can see that we begin to get some more fill in our operator. And finally, we have root node, which is a method worked on by my advisor Luke Olson and Jacob. We start with the same tentative prolongation operator from smooth aggregation, but before we do anything else, we rescale this to get ones at the coarse points. So one of the big things you'll note here is that in classical AMG, we only had coarse and fine grid points. In smooth aggregation, we had our red aggregate and our blue aggregate, and in root node, we have both. So we're defining coarse points on top of our aggregates, and we're requiring that they be taken to the coarse grid through injection. So we improve using energy minimization, and then we can note that our injection is indeed at the bottom. And then finally, just to note that this would be the ideal P given these two coarse points. So it's not the exact same, but it's certainly an approximation to it. All right, on energy minimization, so ideally we want a P with low energy and also with low complexity. So the energy minimization ensures that not only do we minimize each column of P under the energy norm, but we also require P maintains a sparsity pattern and that the coarse grid be exactly interpolated, to the fine grid via injection. Okay, so one quick thing to note about this is that the more coarse points you have, the bigger your identity matrix is going to be on the bottom. So that's going to give you a sparser prolongation operator in the basis function. So if you just look at a single basis function, the range that something could be non-zero is very small. When you have fewer coarse points, the range at which a basis function could be non-zero is greater, and how much of that fills out is going to depend on the problem at hand. All right, so in terms of numerical experiments, we looked at the ideal prolongation operator in terms of both the classical CF splitting and also by using a root node approach where we define coarse points on top of our aggregates. We look at classical AMG, root node, and smooth aggregation. And one thing to note here is that a key feature of root node is combining basis functions, and we don't do this here because it makes it easier to visually interpret the prolongation operators we get. The problem sizes are small, so you could think about this maybe as a computational thought experiment because it's hard to run p-ideal for big problems. It's a V11 cycle with the pseudo inverse on the coarse solve, and the relaxation is symmetric Gauss-Seidel. The setup phase, all of these problems use a classical strength of connection measure with theta equal to 1/4. It's important to note that we could do more parameter tuning for these models to maybe get better results, or these methods, but we try to use out-of-the-box parameters and just see how well we can do against p-ideal. We do improve the near null space candidate, which is the constant vector, and in SA, or smooth aggregation, we improve the operator with Jacobi, and with root node we use energy minimization. All right. So this is our first set of results for the Poisson problem. You'll note that with the ideal prolongation operator and classical AMG, they're right on top of each other, and you'll also be able to see that the prolongation operator is exactly the same. Here, root node and smooth aggregation do slightly better than the ideal prolongation operator, although it's certainly very close. This is what the operators look like visually. So I've just plotted one basis function of P on a 30 by 30 grid, or the problem domain. This is the ideal P with the aggregation splitting, and you'll notice that there's more detail down at the bottom. Root node does look like a good approximation, and actually the ideal prolongation operator from the classical CF splitting and classical AMG look very similar. The reason that the operator complexity is so much higher is because when you're forming the inverse, you can introduce very small, close to zero terms, and after I formed the inverse, I didn't drop all of those very small terms out. So had I been more careful, we could have lowered the operator complexity, so just something to note there. Oh, and actually, I do label how many C points are in the operator. So in the top, there'd be a 17 by 17 identity matrix, and in the bottom, there'd be well, it's not 50 by 50, it's 50%, so whatever the total number of points is, 50% of them would be handled via injection. All right, so for isotropic diffusion, we have similar results again. Everything converges well. There is some slight gain from root node, smooth aggregation, and classical AMG, although again, very, very close. And these are the prolongation operators here. So root node looks very similar to P ideal. You're just constraining the sparsity pattern almost. Smooth aggregation looks different, but still converges just as quickly. Same convergence factor right here. And then there is some difference between the ideal prolongation operator with the CF splitting and what you get with Ruger-Stuben. The convergence is very similar. The operator complexity wouldn't be quite so different, but you would expect it to be somewhat different given the bottom. Looking at scaled isotropic diffusion, so we took the same problem we had before, but we scaled it with a diagonal matrix. This definitely messes up some of the convergence. Classical AMG slows down, and root node also does as well. It's important to note that root node forces the near null space candidates to be exactly interpolated, and for a scaled problem, this might not be an advantageous assumption or constraint to be upholding. So definitely something for us to look into more in the future. P ideal is right between root node and the smooth aggregation, and then it also does very well for the CF splitting. This is what these basis functions look like, so not quite so nice. And again, that's because the problem's scaled. And again, you'll see that there are some main points of the operators that seem similar with classical AMG and root node, and smooth aggregation has quite a different scaling, but still performs very well, and in fact performs the best for this problem. So it looks quite different than P ideal, but it has the lowest convergence factor. And finally, not finally, so we have anisotropic diffusion, and this is the one where P ideal really shines. It's doing quite well, or better, compared to root node or smooth aggregation, and it also does much better than classical AMG. And when we look at the basis functions for this, we can really see how nice this ideal prolongation operator is in terms of finding the smooth error in the anisotropic diffusion problem, and it does much better than root node NSA. If we smoothed on root node more and released the sparsity pattern, we do recover something that looks very much like this operator, and then the convergence of root nodes speeds up as well. But I held this to a modest sparsity pattern because in practice we wouldn't want to create a very dense operator. So the last problem is linear elasticity, and this is the problem where we get some kind of strange results. Root node, smooth aggregation, and actually both of the prolongation operators from the CF splitting do well. But then the ideal prolongation operator from the root node CF splitting trails off and actually we can kind of get a sense of why when we visualize the operators. So recall that I mentioned in the beginning that the more coarse points you have, the larger part of the matrix is going to be the identity, and that's very nice. Here, when I looked at what was happening, in the aggregation-based methods, we're able to form very few aggregates, and so there's actually only a couple of coarse points, because there's one coarse point in every aggregate. So essentially, P here has only 5% of the coarse points being interpolated, only 5% of coarse points, only 5% of points are coarse, and so they're handled via injection, and that means you have a hefty portion of the operator that gets filled with negative AFF inverse AFC, and we really see that in this case, the majority of the non-identity part of the prolongation operator for the ideal prolongation operator is non-zero. And this notion where getting rid of small entries can help convergence has been seen before. It comes up when you're trying to parallelize a method and you're removing sparse entries and you notice that convergence is still acceptable. So that could have something to do with why root node and smooth aggregation do quite well. It could be that removing these interpolation weights doesn't really matter, and in fact could even help. It also probably limit the potential for rounding error because you're doing fewer floating point operations. All right, so in summary, we have found that the ideal prolongation operator does seem to minimize the weak approximation property, although it's very close. And here I only compare between root node and the ideal prolongation operator from the aggregate, because that's the one that's been scaled appropriately. There does seem to be something happening with linear elasticity. All right, the ideal prolongation operator often requires more work for digit accuracy. This wasn't so surprising, and it probably would have looked a little differently had I been more aggressive about constraining the ideal prolongation operator and making sure that nothing close to zero was held. And then finally, the ideal prolongation operator does not necessarily converge more quickly. We notice this in particular for smooth aggregation. And then here, both root node and smooth aggregation perform better in terms of their convergence rate. So extensions, you already got a sense yesterday that the ideal prolongation operator is really defined in a certain manner, and that when you redefine how the characteristics of restriction and prolongation are derived, you can get something better. Actually, the near null space candidates were kind of brought up in the sense that if you incorporate some of these eigenvectors associated with small eigenmodes in your derivation of P ideal, it seems like you could do better. And so it seems like it would be advantageous to think about this in terms of smooth aggregation, and that would be why we do see some improved convergence for the aggregation-based methods. Finally, I'd just like to note that balancing the number of coarse points and the number of entries in one column of a prolongation operator is give and take. And so it's interesting to think about where that ideal lies, like how many prolongation basis columns would you like, and how sparse would you also like them to be. All right. So thank you, and I'll take any questions.